afternoon, and welcome to our third and final event of the 2021 Spark Speaker Series, hosted by Incom Payments, live from our Go Studio headquarters in Atlanta, Georgia. For those of you who are joining us for the first time, Spark by Go Studio is a motivational series of speakers who are all respected authorities in their fields and have been invited to present unique emerging technology use cases that will continue to shape the future. I'm Kelly Barganier, your Master of Ceremonies for this exciting adventure into the world of cutting-edge technology solutions. Now, before we get started, I'd like to share some background on Incom Payments and Go Studio. Incom Payments is a global leader in innovative payments technology, delivering enhanced end-to-end payment platforms and emerging financial technology solutions that help businesses grow across a wide range of industries, including retail, healthcare, tolling and transit, incentives, mobile payments, and financial services. So some of you may be thinking, well, what is Go Studio? Go Studio is Incom Payments' in-house innovation center, where the Go Studio team joins Incom Payments employees, outside clients, and business partners, students, and academic partners to explore emerging technology solutions. The Go Studio team really pushes the boundaries, focusing on solutions with technology that might be 3 to 5 years away from wider adoption. Things you may have heard of, such as blockchain, digital twin, AI, computer vision, and more. By continuously exploring applications of emerging technology, such as the one we're here to discuss today, we can discover, define, disrupt, and solve problems to enhance our clients by introducing these breakthrough technologies. Now let's get started unraveling the mysteries around AI and machine learning technology. This technology is a hot topic right now, and most companies are either working with it or evaluating solutions. With the amount of information that's out there right now, one can easily become lost and overwhelmed. That's why the Go Studio has invited Dr. Roy George, Professor and Chair of the Department of Cyber-Physical Systems at Clark Atlanta University, to join us and help guide us through this very exciting and innovative technology solution. So please join me in giving a very warm welcome to our guest of honor and keynote speaker for today, Dr. Roy George. Hi, Roy.
Oh, hi, Kelly.
Thanks for joining us today at the Go Studio. We're excited to have you.
My pleasure.
Great.
I'm happy to be here.
Yes. Well, I'm sure there's going to be questions about AI and machine learning, and Roy is ready to answer as many of those as possible. Just post them in the Q&A at the bottom of your screen at any point during the presentation. So without further delay, Roy, I'll hand it over to you.
Okay. Thanks, Kelly.
Sure.
Well, good afternoon, everyone. My name again is Roy George. I'm a professor in the Cyber-Physical Systems Department at Clark Atlanta University here in Atlanta, Georgia. And I'd like to thank Incom and Michael Parlato for inviting me here just to talk a little bit about some of the recent advances that you have seen in this field of artificial intelligence. So today we are talking a little bit more about where do we go from where we are with respect to machine learning. So, we are positioning ourselves a little bit further out into the future, assuming that machine learning is something that is going to be widely adopted as we see the trends today. So as always, whenever I start one of these things, it is good to start off with a sort of a lame joke, and this is my lame joke for the day. And for practitioners in this field, really, this, even though it is sort of in a lighthearted tone for practitioners in this field, really this is something that is a reality, that you see the capability of this technology being democratized and being deployed across from, say, 10 years ago, where we had the IBM Deep Blue. Now it's come down to your laptop and your cell phone. So this is where we stand. So very often practitioners in this field seem to be in the same position as the scientist you see here. So, so where are we today? You know, over the last, I would say, 5 to 10 years, this machine learning theory has rapidly expanded and is being practiced. You see theory and practitioners throughout the world expanding and expanding its boundaries and frontiers. So, so just as a little aside, I was attending a meeting recently, and there was something that was happening in the city-state of Singapore. They said in the last 3 years, the universities there with industry had fielded over 4,000 applications in machine learning in a period of 3 years. So this is really the pace at which it's expanding is really very rapid. And of course, with this rapidity, it's no longer the big organizations like your Googles or your Amazons, but it has come down to, I would say, almost to the level of mom and pop stores. You know, everyone needs this. So we are at this point with the infrastructure and enabling technologies such as cloud in a much better position to handle what used to be the big 4 V's of big data, the challenges, that is the volume of data, the velocity at which it is coming, the variety of data, and also to some extent we are able to handle the veracity of the data, that is the truthfulness or how much you can believe. But even with this, we have several issues with where machine learning is today. The first and foremost is testing is difficult because we are dealing with a statistical and a knowledge-based technique, and very often the testing is limited to what we know. So you know, sometimes users have an expectation that this, just like say a conventional information technology project, that everything's going to be perfect out of the box. So in my experience, just to give you some idea of this, I had a situation in which where a client gave say several million pieces of data, and we were expected to detect some kind of phenomena which they had seeded five instances of in several million data. So there was a very high expectation from the clients, and from the clients or from people who are adopting this technology. So one of the things that we are also seeing is with the rapid deployment of these machine learning frameworks. So we are at the point now we have no code frameworks, so that say someone with just fundamental or a very basic knowledge of machine learning can use these no code frameworks. But the understanding what goes on behind, you know, so these statistical techniques or these computer science analytical techniques, you know, what is it that is actually driving these? So even for practitioners, sometimes there is some kind of mystery in what lies behind, and especially if you go to some of these no-code environments, you see some results, and it's not always explainable what these results are. The third problem that we have is there are a lot of questions of ethics that we have seen in terms of machine learning. You know, what kinds of data is being presented? What is it learning? Is there any implicit bias in the person presenting these learning data to these techniques? And so sometimes these biases are not very clear. You know, we ourselves are not very. We have no idea of what our biases might be, even if we try the very best, because the data that we have might already be biased, and so we are proceeding with this. And finally, A big issue is we are increasingly seeing regulatory requirements on different aspects of machine learning. So especially when you get into health, finances, who gets, so in health, who gets treated, especially if you have in a resource constrained environment. So say we have instances where health has been socialized in some countries, and so if these products produce health treatment regimes, how does that hit against regulatory requirements of the governments over there? So there are issues of that, and allowing this data and automated learning. All these issues come out in front. So what I'd like to talk today is basically, if we assume that we have machine learning, and to some extent machine learning has been commoditized and also democratized, so it's available to very large numbers of, or comparatively larger numbers of people. So with these issues that I have talked about, is there something more that we can do? So I posit that we have to look at the context in which this machine learning is done. And so if the context is properly used, we can actually mitigate some of these problems that we have seen. And so one of the easiest ways of representing context in the computational or information technology is the use of graphs, because it's the most flexible way that we can represent relationships within a scenario. So similarly with machine learning and for the future of AI, graphs are going to play an increasingly important role. So the marketplace to some extent has seen this, and there are some predictions, as you can see, $2.5 billion by 2024. So what do we get out of these graphs? That is, we would like to see these relationships that exist within data, not just the data that's used for machine learning, but if you take this data that's used in machine learning and place it in a wider context. So what might this look like? So let me give an example there. So for example, if you're looking at transactions in a bank, so the people deposit money, people take out money, you take out a loan, you repay your loan. So there's this constant set of transactions that happen in a bank. So typically what we are doing in machine learning is, so if we would like to uncover fraud, for instance, so we would take this data, which is at the point of being a little technical, which is relational data. That is, every piece of data has the same length and has got some certain attributes to it that have known and predicted properties. So we would take that kind of data and sort of do some kind of a machine learning on it, and then we are able to predict fraud. But there is a wider context. So beyond this transactional kind of data, what is the wider context in which this happens? So if we have fraud, where is it occurring? Who are the people perpetuating this fraud? What are the relationships that they have with other people who bank at the same place? With merchants, is there some aspect of a bank that makes it susceptible to fraud, or a branch of a bank? So these are the kinds of relationships we would like to uncover, and using a graph-based representation, I would suggest that it is a lot easier to uncover those kinds of aspects of the problem compared to just looking at transactional data. So this is just one aspect of it. Other aspects of it is, say we have, again, people connected and machines connected, so computer programs connected. So there are a lot of instances in which we would like to see how information disseminates through this. So it might be used as part of a machine learning program. For example, we would like to see how some certain decisions are made. But how these decisions are made, or we would like to do some kind of predictions, but how these are done has to be looked at in the context of this whole setup of network of people, machines, and sensors, whatever we would like to throw. So the relationships, so the bottom line for all this is that the relationships in data are just as important as the data itself. And recently, actually earlier this year, the Gartner had come out with a little note which sort of indicated this stuff, that out of, I guess, 2.5 quadrillion bytes of data that are being produced daily, about 50% of it is immediately stripped of all kinds of associations. And so we have this set of data which is literally not workable with. So a better representation in conjunction with machine learning and AI would lead us to better decision making. Okay, so these are some of the benefits that you can a graph-based approach can deliver. So so one of the things that we have seen with the ongoing pandemic, and also I've read that out in several places, that some of the discoveries with respect to the vaccine might have come out of this graph-based representation. Definitely with law enforcement and intelligence, and later towards in the latter part of this talk, I'd like to actually discuss one of those law enforcement problems that we have worked on. The other aspect of it is things like hyper-personalization. So we have product recommendations, but we have been in the process of doing product recommendations for a long time. So we see it on Amazon or on Netflix. But product recommendations also have to be looked in terms of your supply chain. So a product recommendation is made, and someone buys this product, and they have to return it. What does it mean to the supply chain? So as you go from a basic problem, as we extend that out into this modern interconnected world, the machine learning becomes a piece in the larger puzzle. The larger puzzle, I would suggest, would include this graphs and AI. So by that same token, I've already talked a little bit about fraud prevention. That is, if we have fraud occurring, how does it fit with the environment? What are the interrelationships between the entities that take part in that environment? So, and the last point is, of course, in terms of data integration. So we would like, say, on demand, find data, and data that is the most valid and the most has the most veracity. So it is our old problem where we are trying to integrate different sources of data. So all this is through this idea of networks. Okay, so fundamental to this, and I will not belabor this point too much, is all this comes out of the initial bridges of Königsberg problem, where there were seven bridges, and the idea was, could you walk across these 7 bridges and never cross the same bridge twice? So that is where graph theory and networks, actually the idea behind graph theory and its practical implementation networks actually started. And Euler actually described this theorem by which you could figure out whether this was actually true. But what we see today is, wherever we look, the this kind of data is in plenty. So we have event graphs where maybe we have causality between events. That causality would mean that we have an event happening and this kicks off something else, and there's a cascade of events, or just the relationship with among events and components of the events themselves. So the other pieces like computer networks, disease pathways, food webs, underground networks, these are all things that we see in our daily lives. And the important point that I would like to make here is that we have data that has to have this flexible kind of representation. Okay, so if we have that kind of data, at the same time we would like to employ AI and machine learning, is we have to sort of make these two things, or these two aspects, that is flexible data representation, coexist with our ability to do machine learning, or at a larger level AI. And so this data is what will force us to bring in the ideas of context into this problem. So just quickly, we have, of course, the biggest network that, one of the biggest networks that we can see, social networks, 1 billion plus users using Facebook, and other things like networks of neurons, which basically is a signal pathway that exists within the human body. So how do we model it? How do we change it? How do we identify its mechanisms? These are of all interest to medical researchers, and also I would say to us, because eventually this comes out in terms of new mechanisms for cures. So as you see, these networks are everywhere, and so the conventional notion that we have of machine learning, that is, I would say the base notion of machine learning, is not sufficient to take all these things into account. And so what I would like to talk about in this slide is some of the companies that are using this idea of networks, machine learning, and as we go ahead, you see the popularity of these kinds of approaches is pretty large. Okay, so this brings me to the main aspect of this talk. So in an organization, how would you deploy these networks or graphs? So how would you incorporate machine learning into this? And so that's the roadmap, and the bulk of my talk is going to be. So this the slide over here actually shows from a starting organization all the way on the left-hand side with knowledge graphs, and then we proceed through graph analytics, feature engineering, and finally we come into this idea of embeddings and graph learning. So at the right-hand most, where we get into graph learning and native learning, we have achieved the full integration between graphs and machine learning. So starting out with small enhancements to our representational schema, all the way up to graph learning, which is where the bulk of the work going on. There's a lot of interest going on especially with graph neural nets, which is basically, again, using graphs and neural nets. There's been a lot of activity in that field in the last 2 or 3 years, and there's been quite some interest going on. So in the next few slides, what I intend to do is just talk about these different aspects of graph deployment for an organization, and also we will talk about some applications that they might be used for. So it might spark some interest to some of my listeners. So maybe you can think of deploying this in your own scenarios. So the first and the most simplest is what's known as knowledge graphs. So basically what we have on this left-hand side is a knowledge graph of a banking application. So we have these account holders, banks, social security numbers, phone numbers. And so what we are trying to do here is see by simple pattern recognition whether we can extract some information out of this. So if I'm looking at, say, the account holder in the middle, how many hops does it take for me to get to another account holder? So if I'm looking at the guy in the middle and the guy at the top left-hand side, so there's 2 hops. It goes through the home. So both these people have the same home address. So through identification of these hops, you can add simple metrics to your machine learning problem. So you might see some things that might constitute fraud here. People are sharing phone numbers. Different people share the same social security number. So it becomes, by simple querying mechanisms, we can actually gain quite a bit of information, and we have not wandered too far from what we are used to. So all that we need to do is take our data and put it into knowledge graph representational form. So if you're looking at this, just to formalize this, so we are looking at things like how many flagged rings, how many flagged accounts in the network, rings of connectivity. So rings of connectivity would be important in, say, if you're looking at a money laundering application. So Joe gives the money to Tom who gives it to Mary, and so that we are able to trace these patterns. And so some of these things we can actually, through the addition of simple metrics to our machine learning process, we can incorporate this idea of context in there. So of course, this slide says we have to choose the correct representation of what we are trying to do. So the network has to have, so whatever you're representing has to represent your scenario. So if you connect individuals that work together, it becomes a professional network. If it's people who share hobbies together or who socialize together, it becomes a social network. So that's one of the keys, the representational part of it. So the next step in this chain would be where we are actually looking at network analytics. So that is, if given a network, so if given some data, if we are able to convert it into a network. And typically the way that you would convert it to a network is just by looking at commonalities between data. So everyone who works for Incom would have a connection to Incom as being the place of employment in common, even though they might go to different educational institutions, or they might send their children to different schools. There is a point of commonality. So anytime you have these different data that might be relational, you can always convert that into a network by tracing out the commonalities. And once you have the network, we can do this. We can do analytics on the network, and we take these analytics and we add them as part of our machine learning process. So we have this big jumble on the left-hand side. So what we are looking in this is what kind of relations exist within this data. What is the significance of these connections? And if we are looking at something more complex, how does the network change in time? So we have a couple of ideas about networks. What constitutes a network? We have nodes and edges in a network. And of course, the network can be of complexity, that the edge between two people. So say Tom knows Mary, but Mary does not know Tom, so it's going in one direction. Or we could have Mary and Tom are connected to each other. And also, we could have the network could get a little bit more complex. It could be weighted versus unweighted. That is, for example, if I'm calling my friend, say Tom, so I call him 3 times, so the weight of that link would be 3. I email him 6 times, so the weight of that link would be 6. And so what happens is that the connection and the weight of the connection between people changes according to the scenario that you're looking, and that gives us a lot of insight into what is going on in this network. So, so some of the other companies that have, of course, used network analytics, Goldman Sachs, PayPal, the Bank of England. So, there is this idea that doing an analytics on this kind of networks actually deals or gives you a lot more insight than would give, say, point data or episodic captures of data. So for example, you know, the fact that I have deposited funds into my bank 5 times this month has to be looked at in relation to who all are depositing money in the bank. Am I the one that does the most number of deposits? So what is my connection to Tom, who has deposited 100 times? So this is sort of what I would say, it's sort of an artificial scenario that I've given, but you can take that idea outside and apply it to your own scenario. Okay, so I'll just skip this. Okay, so what happens in network analytics? So basically we have a network, and then we compute a set of statistical properties out of the network. So one of the most fundamental properties that we have is in terms of centrality. So if given a network, can we identify the people or the nodes or the machines that are central to this network? So if you're looking at, say, the internet, you would probably see centrality, the routers deployed by these big telecom companies as being central to the internet, because that's where a lot of the routing is taking place. So similarly, we can do it in a social network. You know, who are the important people in the social network? What is the order? So you know, one of these ideas that we have today is the idea of an influencer. So an influencer could be a centrality mechanism, although it would be sort of a crude centrality mechanism, but it's a centrality. It shows the importance of a person in that network. So also the other point that we're really interested in is what is the distance between people. So remember, this is all in a virtual. These are all virtual distances. These are not like distances on the highway, because I could be my distance between me and someone in Japan could be much shorter than me and, say, someone here in Tucker, Georgia, okay? Because I don't communicate with that person at all, or I communicate once a year to wish them, say, Happy Thanksgiving, whereas the person in Japan, I talk to him 6 times a day. So the idea of distance also becomes important, because again, what we are getting is that. So imagine a network like Facebook. So we get an idea of the distance between people, and so immediately this opens up things that you could do. So if you know that I'm close to Tom, maybe I would be the best person to send Tom a message, because Tom is probably more influenced by me than, you know, Jane out there. So in terms of distance measures, we have several different types of measures, shortest paths, and so the things that we did maybe when we were doing algorithms a long time ago, in our undergraduate days. So some of the centrality measures that you see is, the first, the most important one is of course called PageRank, and that's what Google, that was Google's initial claim to fame, that they were able to take all the pages on the internet and assign a rank to that by some computation. And so if I looked for prepaid cards, I would immediately get income because that was the most important page as far as PageRank was concerned. So similarly, we have variations of this PageRank closeness, and I will not belabor the point, but the thing is that we can, if given a complex situation like a network that exists, so we apply these algorithms, get these measures, and we can then start using these measures in our machine learning process. So what we have done is we are again employing the context of these networks into our machine learning process, and that is actually what I would like to tell you all today. So we have, in terms of financial applications, people have used it for a host of these applications. So even things like anomaly detection, fraud detection, system monitoring, system risk analysis. So all these things allow themselves to this network applications, and you see companies increasingly using this. So similarly, again with compliance, also in terms of criminal investigation, terrorist networks, policing, money laundering, all these things. So if we are able to, again, take a network, establish who the critical parts of the network are, then we can begin to look at it in terms of other machine learning problems. So one of the applications that my group has done is looking at using network analysis in a data set that involved Bitcoin-based money laundering. So how do you determine whether a transaction or a node has engaged in money laundering? And so what we did was actually extract these measures, network analytic measures, out of that of the larger network we had, and apply it in a machine learning problem. So we can also do the reverse. That is, we can say have a regression problem, which is like a prediction. What do I predict? What am I predicting the value of some stock? So what is IBM's stock price going to be tomorrow? I can put it in the context of a network and also have my network capability enhanced through these measures. So in fact, these network measures, recently we have seen the Panama Papers and the Pandora Papers. People have actually taken these network analysis, and this of course is just a very basic representation of them, but using this representation, they've been able to find who the key players in this might be in things like global evasion of taxes. So the third step along the way. So previously, the first two steps, the first one was a knowledge graph, where we said, okay, we are going to get some simple heuristic measures out of it and put it into our machine learning problem. The second one was where we were computing statistics out of these networks and putting it into a machine learning problem. So now we are getting to a point called graph embeddings. So in graph embeddings, what we try to do is we are thinking of, can I take the node and its structure and convert it to a feature vector? So almost like what we have done in machine learning. So in machine learning, we are using feature vectors. And so the question now becomes, can I use this? Can I do the same thing with these graphs? And so what you can see now is we are taking these graphs and converting them to a normative structure of a set of features. And so this now becomes directly, we can directly embed it into a machine learning program, whereas previously we were computing things that were external, that is external on the graph. We're computing it and putting it into our machine learning problem. So something that actually feeds into the graph embeddings is also the idea of information diffusion. So if you have a network like previously, how does information flow through this network? So of course, with this has got important applications in social networks, marketing, of course, cybersecurity, insurance, and banking. That is, given a structure of a network. So if you can imagine, it's quite interesting what happens here. Given the structure of a network, we are looking at, say, Facebook, for instance. So given Facebook, if I seed information with John here sitting in Atlanta, how is this information going to spread through that network? Can we predict that? So as you can see, there are a lot of business and commercial applications to that, because now this idea of even viral marketing becomes sort of has a quasi theoretical background to it. So these are two aspects of where we are looking at graph embedding. So using the information diffusion, we can actually move into these node embeddings. Okay. So the last part that I want to talk about is, can we predict what these graph components are? So we are moving directly now. So all the three techniques that we did, knowledge graphs, network analytics, and node embeddings, they were sort of not native machine learning on a graph. So the question now is, can I do machine learning on the graph? That is, without any intermediary techniques like centrality measures or node embeddings. And so once you start doing this, you can actually do things like, can I predict what a graph does? And why would I want to predict what a graph does? An example would be looking at the structure of a molecule that has somehow been created. Can I predict how it smells or what its therapeutic properties might be? So again, it is a machine learning problem. All that we have is our representation of our data is completely different as opposed to a conventional machine learning. So we have this same thing at the node level. That is, can I predict a node to be have been employed in money laundering versus a node that is, that's legit. And the last one is at sort of at the edge level. That is, if I have two people come, or if I have a network, and if a second person, a new person comes in, where in the network would this person attach themselves to? Okay, so these are all typical decision problems that we have, except now it's in a network and not necessarily in relational data like I talked about previously. So that actually brings us to the question of graph learning. And those of you who are familiar with deep learning and have done deep learning on neural nets, this is a very hot topic. From my understanding, there's probably only like 1 or 2 books written about it. It's mostly papers. So basically what we're trying to do is, can I take a network structure and feed it directly to a neural net? Now, conventionally, this would not be possible because, again, a neural net is expecting certain kind of regularity in structure, and a network does not have regularity in structure. It is all depends on who the participants in the network are, what their connections are. So each network could be completely different. So here, what we're trying to do is natively, can I do deep learning on the graphs? And people, so the researchers have actually started working on this, and the expectation is that this kind of work, 2020 and 2021 have been very, very active years for this kind of work, and it is expected that in another couple of years we're going to see a whole host of applications which does not require any more intermediaries like the knowledge graph or the network analytics or even node embedding, that we would directly be able to do all our learning directly on these graphs. Okay, so I just have a little plug for some of the work that my group has been doing. So we are actually have what we call a graph machine learning architecture, and so the outputs of the graph and the outputs of the machine learning, we would consider them to be sort of first-class data objects which can be transferred back and forth. And so this is something that we have been working on so that we have sort of a no-code environment for us to do both graph learning and machine learning at the same time. So one small application that we have is that we worked on was using this architecture to mitigate the effects of fake news. So the application that was given was we had this misinformation and disinformation happening in Eastern Europe, and basically a US government agency was trying to do some kind of humanitarian COVID-19 related operations. And so we are able to actually apply these kinds of analytic solutions to mitigate the spread, basically by understanding the paths through which this information spreads, understanding what messages are actually fake as opposed to real news. And so if you think through the use of optimal pathways, it gives decision makers some ways to counteract these messages. So the idea here is that we have a network, we have information spreading through this. A closer look at the network using some of these analytical techniques shows us where we could possibly firewall the network. And so this was some work that was done last year, and now what as this idea of fake news actually has taken on another aspect. They call it cognitive warfare now, and basically the idea of cognitive warfare is just the destabilization of societies using well-placed misinformation and disinformation. So the same ideas can be applied to there, because by using these analytics on these networks, or machine learning on these networks, what we find is who are the people who are most susceptible to this, or who can we wean away from getting into this morass. So how do we firewall parts of the network? Not necessarily shut things down, but by giving perhaps opposing viewpoints at an early enough stage might be enough. Of course, at some point, psychologists and the social sciences also have to come into this equation. It's not a purely analytical solution. Okay, so some final thoughts about it. So I hope through this talk you have been able to see that context machine learning, of course, is a fascinating new technology with a lot of advances going on all the time, continuously. But context in this is vital, because the context would permit better decisions from them. So rather than looking at it as just data, a snapshot of data, and us making a decision on that, the ability to apply context can give us better decisions. And of course, how does it give that? That is through implicit information. And as an organization, what we have to consider is we have to look at a continuum of approaches. That is, we are looking at from very simple things like knowledge graphs all the way up to graph learning. So there is a continuum of approaches which have to be employed, based on your maturity of your organization and the experience of your personnel. So algorithm development, we have no code environments in machine learning, but at some point, these as I hope I was able to convey this to you. There is only this far we can go with these no code environments and off-the-shelf kinds of platforms. So at some point, we'll have to look at developing algorithms which incorporate these various techniques. There's definitely a place for no-code graph machine learning environments, because that really is a quick start. You can jumpstart your journey for your organization through these no-code environments. But as you get more sophisticated, that's where you might have to go back to these algorithm development. And last and final, when we look at these real-world graphs, situations that exist, Facebook or any other kinds of social networks where you have billions of users, scaling this machine learning also, scaling in general is a challenge, and that's something I think all of us will be working on for quite some time to come. So with that, with one last plug for Spark by Go Studio.
Roy, great presentation.
Okay. Well, thank you, Kelly.
Thank you so much.
You're welcome.
So much great information that I think I'm really glad we recorded this session, because I'm going to have to go back and rewatch it, and it feels like one of those movies I'll learn something new every time I watch it. So I'm really glad that
thank you.
You just shared so much valuable information. And it's interesting to see how it applies to our everyday real life scenarios. Like you mentioned, the social networks, and how is it that I'm having a conversation about wanting to take a trip to Jamaica, and all of a sudden I'm getting coupons and discounts for taking my trip to Jamaica. So now I know we have a lot of burning questions that everyone has around machine learning and AI. So if everyone can enter your questions into the Q&A now. In the meantime, I've got a couple of thoughts to kick us off.
Sure.
So the obvious question, what business do you think has leveraged machine learning and AI, and why do you think they've been most successful with it?
Okay, so I would say, the big three, like Microsoft, Google, Big Four, Amazon, and Facebook, they have been very successful with machine learning. Of course, they have both two aspects of it. One, of course, is the commercial and generally available, and also on the other side, they have their research teams exploring this. But I think the key to their success has been the fact that they started getting into the cloud, and so you started assembling all this data, and so once you assemble the data, immediately the question comes, what else can I do with it? So I think that was probably the aspect that made them that successful. But continuing forward, I think it's going to be the financial companies, because everything ultimately comes down to how much money you can make off something. So I would think that so when we went through these examples, you see a lot of financial applications getting into these graph technologies, machine learning, the combination of these two. And that's because there are drivers. One is the reward, and the second part of it is also the regulatory compliance. So you have, say, if I want to send money from Atlanta to Cape Town in South Africa, so so the way that the banks do it is if a bank here does not have a direct line to Cape Town, they take paths in between. So they send the money from here to Frankfurt, from Frankfurt to Dar es Salaam to Cape Town, whatever it is. So now typically the way that the banks would operate is they look at the path that has got the least cost. But now the problem is because of regulation. If one of those guys somewhere in between is on the U.S. government's list of bad guys, you are held responsible for that. Even though you had no idea, because it was being done through some algorithm or the other. So what's happening is compliance, because of compliance issues and the need to automate some of these things, rather than have a big compliance part of your organization. So I think going forward, they would be really very innovative in coming up with new products and approaches.
So you don't want to show up on multiple graphs from financial to the detective work as well, right?
Yes,
Being connected to the wrong networks.
Yes, the wrong networks, yes.
Well, let's see if we have any questions that have come up here from the audience. Here's a great question. What are the key differences between machine learning and AI?
Okay, that's a good question, and the answer is not that that clear cut, and I will give you my interpretation of this. So machine learning is the use of I would say statistical or computer algorithm based solutions to data that is given to you in some predictable form. So AI, on the other hand, I would say is a higher level of learning where you are able to solve problems that go beyond beyond data just being presented to you. So maybe it can encapsulate some experiences of people, the context. So that's coming back to our graph theory. So I would say that the AI incorporates machine learning. Machine learning is definitely a subset of AI, but AI has got a lot more other things. It has got the typical things that say we might have learned in beginning philosophy, induction, deduction, all these things which are not necessarily machine learning by itself is not really capable of.
So machine learning can help you present and understand the data. AI can help you decide what you can do with the data, where it can lead you.
Yeah, in a sense, because even through machine learning, you could decide if you have a decision point. So is this do I give this person a loan or not? That's a decision. That's a decision point. But that's a more mechanistic kind of decision point, right? So with AI, I would say that it is the ability to go beyond this mechanistic standpoint, where true intelligence. So going back to say things like the Turing test, which was how do you figure out whether something is a machine or not when you cannot tell the difference, right? So whereas I would say machine learning still is you can tell that difference.
Sure. So Roy, what would you suggest, or what could you recommend to someone who has a very basic understanding of machine learning and AI, and they know it's something they want to learn more about and possibly implement? Could you recommend, other than this fabulous Spark series video, any other resources or references that they could access to get a more understanding of the foundation and learn more about the implementation strategies?
Yes, definitely. These are things that really have been democratized right now. That is, you could be, say, an art major and be a machine learning specialist, whereas 20 years ago you had to build everything on your own. So what I would do is, if someone were that interested, would you have these online massively online MOOCs, they call massively online courses, say like, I don't want to recommend any product, but you have some 3 or 4 of them. So So there are two aspects to it. So one, you can use it as purely sort of mechanistically. That is, you know that this approach can solve this problem. This is the library to implement this approach. You implement it. So once you get beyond that, then I think for a better understanding of what goes on, you have to have some idea of mathematics and statistics. But again, because of the democratization of this, you see courses, machine learning, linear algebra, machine learning statistics, which are not like the statistics in linear algebra I learned back then. This is much more understandable and much more approachable.
Sure.
So I would go in that two steps. First you figure out what we can do from a practical sense, and if that really excites you, you move on to the really theoretical underpinnings.
That makes sense. Well, everyone, that's all the time we have for questions today. But this was a great session and a lot of useful information. I appreciate the helpful insights in understanding machine learning and AI and this technology. So we really appreciate your visit to the Go Studio. We hope you'll come back and visit us again.
Sure. Thanks, Kelly. Thanks again to INCOM for inviting me, and I hope this was helpful.
Absolutely. Well, everyone, we've now concluded the last of our 3 Spark by Go Studio Speaker Series events being hosted this year. Be sure to follow Go Studio on social media, including LinkedIn, for more information on future Spark by Go Studio events in the new year. Now, if you missed either of the 2 previous Spark sessions, don't worry. You can find the full video recordings on the Go Studio's YouTube channel. It has been an honor to serve as your Master of Ceremonies for this incredible journey through the depths of some of the most innovative technologies of our industry today. On behalf of INCOM Payments and Go Studio, we appreciate you joining us for this first series of events, and we hope that they continue to spark ideas, knowledge, and thought you can use. We look forward to seeing you for our next adventures, so until next time.